Hello and welcome to my video on lesson 4.1 on the nature of EMR. EMR stands for electromagnetic radiation, and that basically means light. All different types of light. Light is produced by accelerating charges, meaning it has both electric and a magnetic field, and they're perpendicular to each other and the direction of propagation. So if you look at this diagram that we can see here, we've got the electric field oscillating in this direction, in this plane. We've got the magnetic field oscillating in this plane. And we've got the direction of propagation going in this direction. So the oscillation of the other two are in perpendicular directions to the direction of propagation. Okay, so that's interesting to note. And yeah, let's continue on. So an EMR is a transverse wave, which means that its energy transfer is perpendicular to the oscillation, like a water wave. By the way, the opposite of a transverse wave is longitudinal wave, and that is something we talk about in Physics 20 in mechanical waves. And a longitudinal wave is like a sound wave where it has pulses of dense, let's say if it's a sound wave, dense air, and then pulses of light air. And so you can have that pulse travel through the air. That would be longitudinal, but light is transverse. So its transfer of energy is up and down, while the direction of propagation is this way. Or sorry, the oscillation is up and down, which the propagation, which means the energy transfer, is perpendicular to that. Okay, we often consider waves in two dimensions as it is easier to represent them. So we have this image here, and we're going to label a bunch of different things. So we're going to just start labeling things here. The wavelength is from one point until the same point on that wave. Now this would not be a wavelength from here to here, because here it's going up and it has amplitude of 0. Here it's going down and has an amplitude of 0. So those don't count. It has to be the same position, the same direction. Usually we consider that as, let me just continue the wave along here. Usually we consider that as something that is from peak to peak, or from okay, so peak to peak is that's the one color, or from trough to trough. Those are the easier ones to recognize. Excuse me. But you could go from here to here. Any of those are all one wavelength, from the same color to the same color. Okay? The source is whatever is happening to cause the actual wave. So maybe you have a light bulb. That would be the source of the wave. In the context of water, if you drop a rock, well, you'll see in a second in this next one. Anyways, the direction of propagation is to the right. The amplitude is the height, whether that's here or the height here. Both of those are the amplitude. And the medium is the substance through which it's traveling. So for light, that could be air, that could be a vacuum, that could be all sorts of different things. But whatever that is traveling through, that is the medium. Glass, crystals, whatever. So if we look here at this water wave, and you were to draw this out, it would be looking like this. Okay, one wavelength is from here to here. So I'll call that a wavelength. Lambda. The source is the rock that's in the middle. The medium is the water. Okay, the amplitude is the height of the wave from the center line. So this is the amplitude. Okay, and the direction of propagation is out, away from the source. All right. Continuing on here, we've got a nice image of, this is from Wikipedia, by the way, a nice image showing the frequency and wavelength of the spectrum of light. We've got a few different ones to look at. We've got radio waves, which are very, very long wavelengths. This is times 10 to the 3, which means that it's 1000 meters long. That's 1 kilometer. 1 kilometer long wavelengths. Very, very long wavelengths. And then we go on to microwaves, which are shorter. They're 0.01, yeah, 2, that would be correct, meters, or 1 centimeter. Okay, this is interesting because if you look at the holes, like if you think about an actual microwave, one that heats up food, and you look at the holes on the front of the microwave, they don't let microwaves through because the holes are smaller than 1 centimeter, and that's why they're safe to have your face next to the microwave looking in. I don't recommend that anyway, but you can be next to a microwave and not get heated up because the holes are smaller than that. Okay, infrared is infrared. Okay, it's past red on the visible spectrum. So the visible spectrum has red on one side and blue/purple on the other side. So infrared is past red. We use this for remote controls. And so if you take your phone's camera and point it at your TV remote control, assuming that it's an older style one with an infrared signal, you can see the infrared light turn on because your camera on your phone can actually see a little bit into the infrared spectrum, not just the visible spectrum, which is what humans see. So kind of cool. Some cameras will have a filter to remove infrared, but most cameras don't. So if you check your phone camera, it won't have that filter generally. Okay, visible light is around here, so it's somewhere around, I don't know, somewhere around the 100 or 800 nanometers till I think it's like 380 nanometers. Okay, so it's pretty darn small. It's about the size of protozoans, to give you some ballpark. And then we go ultraviolet. Ultra, so past, violet, which is just another word for purple. Okay, then X-rays and gamma rays. These three over here, past the visible spectrum, these are the ones that can actually cause damage to our DNA. So because they're ionizing radiation. So the other ones, infrared, microwave, radio, they're not very dangerous because, yes, you could heat something up with infrared. That's what you feel when you're next to a fire. You feel infrared heat. Or you can use a microwave to heat up food, especially it heats up liquids, water, very well. But it's not actually ionizing. It's not changing the matter. It's not actually changing the water. It's just adding energy, adding heat. So it's a little different on that side. But the ionizing radiation, that's dangerous because this can cause cancer on this side. That's why Wi-Fi signals on this side, not a problem. On this side, UV, ultraviolet UV, can give you sunburns and eventually potentially cancer as well. So this side is much more dangerous. This is the classic, the Hulk situation. But in real life, you don't turn into a superhero. You basically just die. So it depends on how much of all this you get. A little bit from the sun won't kill you instantly, but it's over time it changes your cells, and sometimes you could have a bad reaction to it. The more you have, the worse your odds are. Okay, so those are all the wavelengths, but what you'll notice down here is that the frequency is actually proportional to the wavelength, but it's inversely proportional. So the frequency is really, really high on this side, so high frequency, and low wavelength on that side. Whereas on this side, it's high wavelength and low frequency. Okay, and energy follows the same as frequency. So energy also has low energy on the radio side and high energy on the gamma ray side. Okay, so yeah, that's basically what I said here as well, just about the energy. This one's interesting as well, that we have something called color temperature. This has to do with black body radiation, and it's going to be more important in the next unit. Black body radiation, this is the scientific name for it, but different temperatures have different colors associated with them based off of that. And so if you look up the sun is somewhere around here. The sun is at about, I think, 5,500 Kelvin, somewhere in that ballpark, is the average temperature of the surface of the sun. And so that's why we have this temperature as sunlight. That yellow/white color to us is sunlight. So kind of cool. It's also why you can buy different types of bulbs, like LED bulbs that do different, basically different colors. We call them different color temperatures. The old incandescent bulbs were about 2,700. Fluorescent bulbs were somewhere around 5,000 to 6,000. And so now modern LEDs, we can pick exactly the right color temperature for whatever we want. So personally, one of my favorite color temperatures, and yes, I have one, is 4,000 Kelvin. It's just the perfect amount of blue and yellow to be not harsh on the eyes, too white or too blue, and yet also not being super yellow and changing the color of, you know, the walls, the carpet, everybody around you. So anyways, my little plug for 4,000 Kelvin bulbs. So the following equations are useful from Physics 20, but we use them also for light. So this is now the change here. We just use this C instead of the V for the speed of a wave. We use C because it's the speed of light, which is the wave. Speed of light in a vacuum or in air is basically the same as a vacuum. So all that information to say, we have two equations here. I would recommend you pause the video now, try the two questions, and see if you get the same answer I do. Alright, so let's go ahead and try this out. Essentially, we're just going to draw a nice picture. What is the direction of the electric field if the EMR wave is traveling towards the north? So this is the direction of travel, north, and has a magnetic field that is oscillating from east to west. So the magnetic field is going like this, okay? Which means that the electric field must be oscillating in and out of the page. So the electric field must be in and out of the page, or another way to say this, because this is north and east and west, it must be up and down. So like literally going up into the sky and down towards the ground. Okay, if I use a purple laser pointer in the air with a wavelength of 390 nanometers, what is the period of its oscillation? Okay, so now what we can do is just go up to this formula here, C equals lambda F. C equals lambda F, and we know lambda, so we're just looking for the F. but the F isn't what we're looking for. Actually, we're looking for the period. So period equals 1 over F. So if we put that into here, it's C over lambda, or another way to write that is lambda over C. So all we have to do is take 390 nanometers, convert that into meters. So 390 times 10 to the negative 9, and then 3 times 10 to the 8 meters per second. This is meters, by the way. And so then we're going to be left with seconds, which is 1.3 times 10 to the negative 15 seconds. Oh, and I just want to point this out. This times 10 to the negative 9, this is in your formula sheet because it tells you nano means times 10 to the negative 9. So that's where that's coming from. All right. I hope this video helped you better understand the nature of EMR and frequency, wavelength of different types of light, and even these calculations here at the end. Hope the video helped, and good luck.